Continuing our discussion on counting, here's an example. An investigative agency has 7 cases and 5 agents. How many different ways can the cases be assigned if only one case is assigned to each agent? So we have a few things to think about. The first thing to consider is whether this is the multiplication axiom problem, a permutation problem, or a combination problem. So let's explore for a few seconds. Let's say we have agents A, B, C, D, and E, just for the sake of simplicity. And the cases, we have numbers. Now, if agent A is matched with case 1, then can agent B also be matched with case 1? No, that's not allowed. A already has case 1, so B's not allowed to have it. Can agent A take on a second case? No, that's not allowed either. One case is assigned to each agent. So how many total cases get assigned? 5 cases get assigned because we have 5 different agents. But how many cases do we choose from? We can choose 7 cases. We have 7 cases to choose from, but we're only going to assign 5 of them. So how do we know which formula to use? Well, essentially, we are arranging these 7 cases to these 5 people. If I assign case 1 to agent A, that's different from assigning case 1 to agent C. So this arrangement is important. The order is important. And we've already established there's no repetition. I can't assign one case to 2 agents or one agent to 2 cases. Those aren't allowed. And when order is important and there's no repetition, this is a permutation problem. So we have total cases. We're only taking 5 of them. So we're going to do a permutation of 7 objects taken 5 at a time. 7 cases, but we're only taking 5 of them to assign to our agents. So how many different ways can we do that? If we set up our formula, 7 factorial over 7 minus 5 factorial. This one's pretty small, so I'm going to do it by hand and then we'll do it on Excel. 7 minus 5 factorial is 2 factorial. 7 times 6 times 5 times 4 times 3 times 2 factorial. We can cancel out the 2 factorials. And we've got to multiply 7 all the way down to 3, which we can. $2,520. That's really big. A lot of different options there. If I pull up Excel here, I can make Excel calculate it. Permute 7, taken 5 of them, 2,520. Awesome. So order matters. There's no repetition. I have a permutation. How about the next problem? Anderson Research Company decides to test market a product in 6 areas. How many different ways can 3 areas be selected in a certain order for the first test? Pause the video, try this problem on your own, and then go check the OneNote and see if you got it right. Similarly with problems 6 and 7, I want you to try these on your own. Go check the OneNote. I will give you a hint. We've got a ranking, just like we have a certain order. These are all permutations. So see if you can use the formula. Figure out what your total is and how many you're choosing. So you're looking for N and R for each one of these. And then put them into the formula. See what you can come up with. So here, the last example in this video, we're going to look at this quick review problem right under our section 4.5. When I created my worksheet, I forgot to check and make sure I had a good representation of all types of problems in here, and I didn't. I forgot some combinations. So let's take a look at this question. Determine the total number of 5-card hands that can be formed from a standard deck of cards. Recall from last week that a standard deck of cards has 52 total cards in them, 4 different suits, 13 cards in each suit. So we're looking for how many different 5-card hands. Here, N, my total is 52, and I want groups of 5, so I'm going to take R to be 5. Now with cards, because when I get them dealt, I don't have to keep them in an order. I have them in my hand and I can move the cards around. So the order in which I receive the cards does not matter. And if order is not important, we have a combination to work with. Okay, I'm going to do the combination by hand and then pull up Google and work through it using Google as the calculator, and know that Excel, the exact same things will happen. So no matter which one you use, repeat the same procedure for either one. So for a combination, we have 52C5, N on top, N minus R factorial, R factorial. And now, as mentioned before, I'm going to do this by hand first. 52 minus 5 is going to be 47. So I'm going to take this top number, 52, 51, 50, 49, 48, 47 factorial. So I'm going to stop at 47 factorial so that I can cancel both of those. And then I have 5 factorial. 5 times 4 times 3 times 2 times 1. Permutations are really nice because in permutations you can just cancel the entire denominator with the last factorial on the top, because you're going to write them down until you stop at the last factorial. But with combinations, we have this extra factorial piece in the denominator because we're dividing out the arrangements with the same objects. We don't want to count ABC the same as CAB. Those are the same according to combinations because order does not matter. So I'm going to try to cancel some in this fraction, and I'm going to use my arithmetic skills. So 47 factorials will cancel. Let's see what we can cancel. So 4 times 3 is 12. And 12 times 2 is 24. I know that 24 will divide 48, so I could cancel 48 and 432 and be left behind a 2. 24 divides 48 and leaves a 2. This is just one example of how I can cancel stuff out. There are multiple ways you can cancel factors. So I canceled out 4, 3, and 2. 1 automatically doesn't matter because it's 1. I divide by 1, I keep it the same. And then the only other thing that I need to worry about is that 5 in the bottom. Now I could multiply this out and then divide by 5, or I notice that 5 will divide 50. And 50 divided by 5 will leave a 10. So what I really need to multiply together is 52, 51, 49, 10, and 2. And if I multiply these 5 numbers together, that will give me the total number of 5-card hands that can be dealt. With combinations and permutations, the denominator, the entire denominator, will cancel with something up top. You will never be left with fractions when you're doing permutations and combinations because we're counting how many different ways can something happen. We can't have a fraction number of ways of something happening. That does not make sense. So let's calculate this. First on our calculator, since we're still doing it by hand. 52, 51, 49, 10, and 2. 2,598,960. Wow, that's big. But that does give us the total number of 5-card hands. Now, by hand takes a lot of time. Let's check it out in Google. And I'm using Google this time essentially because I've been using Excel in the last video. So just to mix it up, using Google this time. Remember that right now Google and Excel will act exactly the same with these formulas. The same formula that I'm entering in Google will also work in Excel, which makes it pretty nice. I'm going to use the combination formula, COMBIN, parentheses. Don't forget your equals out front. The equals tells Excel and Google combining. N comes first. I have 52 total cards, and I'm taking 5 of them. So N, R. And we also get 2,598,960. In our next lesson, we're going to look at using combinations, permutations, and the multiplication axiom to create probabilities. So now we're going to count how many ways a particular event can happen out of how many total ways in the sample space. So again, adding on to what we've just done, but instead of counting, now we're going to look at the probability.